Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on November 26, 2025, just yesterday. This paper shows that large language models do not reliably generalize across difficulty levels, and that training only on easy questions or only on very hard ones fails to produce consistent gains across the full spectrum of tasks. The paper is titled, Revisiting Generalization Across Difficulty Levels. It's Not So Easy. And as we will see later, the implications for how we curate and balance training data are quite significant. Also, the authors shared an accompanying GitHub repo for this work. It hosts the project with a README centered on their cross-difficulty analysis of LLMs using item response theory. Details beyond that are a bit limited from what we can see here, but the implementation is accessible on GitHub. Table 1 maps out how prior studies disagree on whether training on easy or hard examples helps models generalize across difficulty. The table itself lays out, row by row, each paper's core claim, who defines difficulty, and what training method they used. The green rows emphasize benefits from easy data, the red rows emphasize gains from hard data, and the blue rows, including this analysis, stress that generalization across difficulty levels is quite limited. Figure 1 shows that human notions of difficulty barely line up with what these language models find hard. The left math panel plots questions by number of reasoning steps against model-based difficulty bins, and the points spread almost evenly instead of shifting steadily upward. The top right MMLU Pro panel does the same with school-level labels, which again stay fairly uniform across bins. The bottom right ARC panel repeats this pattern by grade, reinforcing that human grade tags do not reliably predict model difficulty. Figure 2 shows how model-based difficulty correlates with traditional human difficulty metrics, and it confirms that these perspectives diverge strongly. Spearman correlation, which measures how similarly two rankings order items, stays close to 0 or mixed in both panels. The left ARC heat map shows only weak positive links between item response difficulty and things like grade, length, or expert labels. The right MMLU Pro heat map goes further, with item response difficulty slightly negatively correlated with answer length and words per question. So human judgments like grade level or longer answers clearly do not track what these models actually struggle with. Figure 3 makes the main claim very concrete. Models mostly help on problems with similar difficulty to what they were fine-tuned on. The left heat map shows absolute accuracy, which stays high along the diagonal but drops as train and test difficulty bins diverge. The right heat map plots improvement over zero shot, and the strongest gains again hug that diagonal. When training on the very hardest bin, the lower left corner even turns negative, so fine-tuning on only the toughest items can hurt performance on easy questions. Figure 4 makes the pattern of cross-difficulty generalization very clear across all 6 benchmarks. The grid of heat maps shows improvement over zero shot, with blue cells meaning fine-tuning helps and red cells meaning it hurts. Most blue mass hugs the diagonal, so training on a given difficulty mostly boosts nearby bins only. The bottom rows, especially in the math and mu-SR panels, turn deep red on easy test bins, which shows that training only on very hard items can significantly damage performance on simpler questions. Alright, wrapping up, 2 takeaways stand out. Models mostly gain on problems with similar difficulty to what they are trained on, and human notions of what is hard often misalign with model-based difficulty. This means training and evaluation data should deliberately span a broad difficulty range. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.